There you go. All right. You don't need to. How's everybody doing? Great. Fantastic. Yeah, well, yes. I was just making sure that the camera is on the board. And this one's far enough back, it gets almost the whole thing. All right, well, I guess we should talk about math. That's why we're all here. So let's do that. Jim is gone today, so that's why he's not here. But that's okay. We can do Math Club without Jim. It's not quite the same. A little more sad, but we'll be all right. Yeah, I guess in my abstract, I said I was going to talk about integrality. And so that is still the plan. I was playing around today with multiple ways to introduce the concept and motivate the concept of integrality. So we're gonna try something. I haven't really thought of it this way before, but we're gonna try it, see if it works. I guess for starters, though, this talk is really heavy in abstract algebra. Has anyone not had an abstract algebra course? Oh, there goes half my talk. Great. Okay, I can skip all the intro. So we're all good if we talk about rings and integral domains. And actually those are the two main things that we'll look at. We're all good with that stuff. Okay. Yes.
I'm currently in it, so we haven't gotten to rings yet.
Okay, cool. Great. That'll give me some things I can say to take us more time.
Okay.
Should all roll down, open the windows that had a Peter Westerbaum as he walks by.
I'll just say it's been a long time since I had algebra, so I probably don't remember anything.
All right, well, let's talk about rings. Why not? Because we can have fun with rings. Basically, the ring is just a collection of elements, collection of objects in which we can add, we can subtract, and we can multiply. When I say we can add, subtract, and multiply, I mean take any two elements in my ring, I can add them together, subtract them, or multiply them, and I'm still in my ring. Right? However, we might not be able to divide. Maybe we can, sometimes, maybe we can't. But so in general, we just don't have that assumption, right? The classic example of a ring, and we'll give a few here. The classic example and sort of the whole idea behind a ring, and actually some of the whole motivation for integrality, is the idea of the integers. Right, so you take the integers, all positive and negative counting numbers, and 0, right? I can add them, subtract them, multiply, and I'm always still an integer, but I can't divide necessarily, right? I can divide sometimes, right? I could take 4/2. That gives me 2 back in the integers, but I can't do 1/2, right? That's a rational number, no longer an integer, right? So we can divide sometimes, but not always, right? So that would be an example. You could have your rational numbers as well, right? The rational numbers we can divide now. So it's actually, if we can throw in division, we call it a field. But rational numbers, real numbers would be similar. Something that would not be an example would be the natural numbers, right? I can add it and multiply, but I can't subtract, because I can, if I do 1 minus 2, I'm -1, which is no longer in the natural numbers, right? So those are some of the basic examples with the numbers that we're used to. We can make them a little more complicated, or not complicated, more fun, right? Yeah, so this is that one. One thing that we like to do is take a ring and then look at polynomials where our coefficients come from that ring. So this would be essentially all polynomials with integer coefficients. That would also be a ring. We could do one of an example that we'll see later. One of Jim's favorite examples is something like this. So I take this essentially is all polynomials where the constant term is an integer and every other coefficient can be a rational number, right? So basically I take, what I do is I kind of start here. This is all my polynomials with rational coefficients. Multiply the polynomial by x. So now its coefficients are only on x terms, and then I make my constants integers. So you can play around with rings and create new ones. This one has a fun property that we'll see later. You can do other things with like matrix rings, and because you can add, subtract, and multiply matrices. So you can do lots of fun things with rings. The specific type of ring that we're going to use today is called an integral domain, which we will primarily just call a domain. I'll usually just leave off the integral. But again, classic example is the integers. The idea with the integral domain is that we don't have what we call zero divisors. So let's give the definition here. Essentially, a times b. There's 2 elements. If the product is 0, then at least one of those is 0. All right, if AB is 0, then either A or B is 0. Right. So actually, in all of these examples are integral domains. Like the integers, if 2 integers multiplied with 0, one has to be 0. Where you might have where this might not be the case is if, for one example of something that's not an integral domain. You look at let's say what's our notation here? You look at this ring, so it's capital M is for looking at matrices. So again, all 2 by 2 matrices where the elements are integers, right? So this would not be an integral domain because you have zero divisors. So you have products like to be kind of simple, but you have products like this where neither of these 2 matrices is 0, but the product itself is 0, right? So when we talk about an integral domain, we would have to rule out examples like that. The other classic examples are if you look at like the integers mod like 4 or something, right? So 0, 1, 2, and 3. 2 times 2 would be 4, which is back to 0. So like they're factors. Okay. Cool. All right. So that's the basics. We're going to get into a little more theory. A little more theory to maybe motivate an idea. We'll see how well this motivation works, because I don't want to go into all the details of why it's important, but maybe it'll help. Nice. Okay, so we like to be able to factor things in algebra, right? Like I can factor 4 as 2 times 2, right? I can take 4 is 2 times 2. And I would say, boom, that's factored. Someone else might come along and say, well, what about 4 is 2 times 2 times 1? Why don't we do that factorization? And someone else comes along and says, well, what if we do 2 times 2 times 1 times 1? Why not that factorization? Right? And the short answer is that, well, we don't really care about the ones, because multiplying by 1 doesn't change anything. It doesn't really help us at all. Right? We could take, well, yeah, let's just say that again. Right? So when we talk about factorizations, right, when we just multiplying by 1 doesn't really affect anything. So we just ignore it. We say, if I want to factor it, I would do this first one, and I would stop there. Right? And if we're looking at the integers, we would call this the unique factorization. Right? We just ignore these ones because we don't care about ones, or technical terms, we don't care about units. Right? 2 numbers we can multiply together to get 1. We don't care if we throw those into our factorization because they don't really change anything. But in some areas, we don't necessarily have unique factorization, at least in terms of what we might call primes, whatever needs to be a prime element. So in the ring Z, where we form polynomials with square root of 5, so this essentially looks like elements of the form a plus b root 5, where a and b are integers, right? Take that ring, for example, and then factor 4. Well, that's 2 times 2, right? Great. But that's also, if I do this one correctly, 1 minus 1 plus the square root of 5 times negative 1 plus the square root of 5. Right? And in this ring that we have, these 2 factorizations are inherently different. I can't sort of multiply this one by some units to get that one, right? These are inherently different factorizations. So we don't want that, right? If we're trying to come up with some results or figure out how everything multiplies and works together, it's nice when I just have one distinct factorization. So we want to get rid of that. We want to get rid of that factorization. And one way you can do this is add more things to this ring so that these guys become off just by a product of units or a single unit, right? So we're going to add things to it. And the way we're going to do that is, well, actually, this is where the example gets a little bit fuzzy. What we want to look at instead is the integers where we tack on 1 plus root 5 over 2. Oh, I guess someone's. So this is where the example gets a little bit fuzzy in terms of actually creating integrality, but we'll try to circle back at the end. Right, so you take now the integers where I tack on 1 plus root 5 over 2, which 1 plus root 5, this will tie in later, so this is a root of this monic polynomial x squared minus x minus 1. You can check that, but it's a root of that polynomial. And this is, let's see, let's not get into that part. But once I include these, right, which this ring contains that one. This one is a little bit bigger because to get root 5 back, I can multiply this by 2 and then subtract 1. Right, so I can get root 5 from this guy. So this ring as a whole contains that one. So I've added stuff to it. And now in my factorization, right, F4 is 2 times 2, which is also 2 times 2 times 1 plus root 5 over 2 times -1 plus root 5 over 2. Because this product right here is equal to 1. Right. And then if I distribute, then I get to that factorization 1 plus root 5 times -1 plus the square root of 5. And so now my two factorizations are off by a unit, so I can view them as more or less the same in terms of the way we call factorizations the same. Right. So the unfortunate part about the example is, right, well, why do we go up here? Right. One way that we can get up there is to look at roots of monic polynomials whose coefficients come from the string that we have here. So in particular, x squared minus x minus 1, right? The coefficients come from this ring, and that 1 plus root 5 over 2 is a root of that. Right? So part of the motivation when I add things, I can get better factorization properties. Yes.
Just, I guess, a question, can you always do this process? Or if I give you an integral domain that doesn't have unique factorization, I always add more so that it does?
Oh, that's a good question. So it's like, I think.
I guess you can always go too far and go to this field, like
No.
this ocean field, but that's like, you're making everything
Well,
good at that. So,
Sure, yeah, so I guess the simple answer is yes, you always can. I think so, if I remember correctly. So when we talk about, we're gonna give it a definition for integrality, but if we have something where we had the unique factorization property and we look for roots of monic polynomials, we can't add anything. It already has its integral closure. I don't remember if the implication goes the other way, but I think it would. That is sort of the whole point of it. That's a good question. I should probably know that, but my focus is actually on almost integrality, which we'll get to in a little bit. So I don't play around as much with the integral. But Jim would know that if he was sitting right there. That's okay. Right. So we're looking at roots of binomials. So let's formalize. Let's give a definition, give some examples, and then move on. I don't really know where this talk is going. We're just doing math together. So okay. Right. Oh yeah. So here's where we get into like history of stuff. Forgot about that. Okay. So this whole idea of factorization, right? Trying to get nice factorization. Some of that goes back to algebraic number theory. So you had this guy, Richard Dedekind. I think his first name was Richard. Back in the 1870s. He was working in algebraic number theory. He also did a lot with just number theory, abstract algebra, pioneer in set theory and logic. Did a lot. Really smart guy. But he was concerned about what he called the algebraic integers. Algebraic integers are roots of monic polynomials where the coefficients are integers. And in particular, they're just looking at complex numbers that are roots of monic polynomials where the coefficients are integers. Right. I guess I threw this out. When I say monic polynomial, I just mean the leading coefficient is 1. Right. So he was doing stuff where he was like, okay, I want roots of these monic polynomials. And then Emmy Noether came along. In the we'll say the 1920s, she did a good amount of work earlier than that too. But we'll say around the time of the 20s, she kind of generalized what Dedekind was doing. So instead of looking at just polynomials with coefficients and integers, she said, look at polynomials with coefficients that come from just a given ring, right? So she gave sort of the classic definition. Of integrality, which we'll write down for fun. Right, so if we have we'll frame it in terms of a domain, but given a domain C with quotient field K, you go with the quotient field?
No, but you can.
Okay. No, that's good. So quotient field is basically all the fractions that you can make.
Okay.
So the integers, the quotient field is the rational numbers.
Got it.
So given a domain D with quotient field K, an element in let's say an element A, K is integral over D. And A is a root of a monic. Monic polynomial with coefficients in D. I don't know if you can read that, but we're looking at roots of monic polynomials where the coefficients are in D. All right, so Emmy Noether was sort of the first one to give the generalized definition. This is even a little more specific than it has to be. So she gave generalized definition. She was actually looking at, surprise, surprise, Noetherian rings, Noetherian domains, which she didn't know they were called Noetherian domains because they were named after her. But so she had sort of a specific context that she was looking at, but she gave a more general definition than Dedekind did. So, okay, so let's pause here on the definition and give some examples of what we want. All right, so when we talk about these elements being integral, if I take the collection of all the integral elements, I call that the integral closure. And I denote that with just a bar over the original ring. So for example, if I start with the integers, if I look at the integers inside this quotient field, which is rational numbers, look at roots of monic polynomials, coefficients are integers, the only solutions that I can get back are integer solutions. So the integral closure, put the name out once here, integral closure which is noted by Z bar, is actually just itself. And the main problem there is that you're looking at monic polynomials. So I can't get any rational numbers to be roots. A result sort of tied to this idea of getting nice factorizations. Any unique factorization domain is integrally closed. So if I take anything where I can factor my elements uniquely as a product of primes, if I look at the integral closure, I just get back where I started. I can't add anything to it. Right. Another fun one, which is sort of covered right here. But if I look at that example that we had earlier, the integers plus xqx, so polynomials where the constant term is an integer, that's actually integrally closed as well. Can't add anything to that one. And the problem really is the integers right there. So if you try to find something that is integral over this guy, the only thing we're really missing are the rational numbers as constants. But once you try to write a rational number as a root of a binomial, your coefficients come from here. So look at the constant term and all the coefficients. And now all of a sudden you're back to a polynomial in terms of the integers, which has no rational roots. Okay. I think we're all on the same page. One more example to show that we don't always just get stuck. That would not be good. This example we'll use later as well. This is actually kind of a famous example. So take a field and add on all these variables, x to the 2n plus 1 times y to the n times 2n plus 1, where n goes from 0 to infinity. So you've got things like when n is 0, you just have x. When n is 1, you've got x cubed, y cubed. When n is 2, you've got x to the 5, y to the 10. And so on. So you've got things like that. Those are your variables that you're throwing into this field. This guy has integral closure F, where we just add on x, y to the n. The idea for that, right? Take x, y. All right. So when n is 1, y is x, y in the integral closure. Well, note xy cubed equals x cubed y cubed, which is in my domain D, right? So in particular, xy cubed is a root of, I guess, the polynomial t cubed minus x cubed y cubed. Right, if I were to plug xy in for t, I get 0. Right, and you can do the same thing in general. Your element x y to the n is a root of, sort of by construction here, x to the, or t to the 2n plus 1 minus x to the 2n plus 1 times y to the n times 2n plus 1. Right. So take anything in here, raise it to the 2n plus 1 power, and you get back in your domain. So those are all the integral elements. And you can do an argument to show that you can't get anything else in there. Cool. Questions? Oh, yes.
What's the quotient field of D? Is it just
Oh.
rational?
Great question.
About division by x and y, or is it not?
Yeah, it's just your irrational functions in x and y. Look at that field. Because
I
you
know
can
you need
get
x. Because you have x in there. but-
right. You have x, and then you can do so once I have x, then I can have like y cubed and y to the 10, and then cube that inside and I get y. Yep, good question. Because you would want to make sure that all of these guys right here are in the quotient field. So that's good. Okay, actually the last statement here to add is that the integral closure is integrally closed. Which is a very nice property. I only have to do this process once, and then I get something where it stops. Right? If I were to take the integral closure of this, I can't add anything to it. I'm stuck right where I am. Right? Which is actually kind of nice. All right. But now, like any good mathematicians, you get an idea like this, and you try to change it, see what happens. And so that's what happened. Let's put this over here. So in the towards the end of the 20s, you had little Wolfgang Krull, who worked with Noether, or at least that's what I had in my notes. Didn't show up in the genealogy project, so not exactly sure if maybe you just had her, or maybe she was his advisor. I don't know, but they were working somewhat together, I believe, around the same time. So he gave this other definition. He gave a definition which is actually equivalent to the one that Emmy Noether gave if you're working in a Noetherian domain or a Noetherian ring. So this definition at first was just another way to define integrality. So he wasn't necessarily trying to do something completely different. He was just like, oh, we can think about it this way too. Right, so he gave this definition of almost integral. And this was, I think his showed up around 1928 or so, right? So the definition, to keep it in a similar vein, we have the integral domain. We have integral domain D, we have the quotient field K, and we say an element A, K is almost integral over D if there exists some D in D where D is not 0, such that dA to the n is back in D for all n, where n is a positive integer. Right. So this definition on its surface looks very different from what's over there. Right. So I got an element in the quotient field and some element in my domain that sucks all the powers of that element back into the original domain D. If you look at this in a Noetherian context, these definitions become equivalent. There's also a way to format both of these definitions in terms of modules, which makes it even a little bit easier to see how they are equivalent in the Noetherian realm. But so this was his definition. And then he was like, oh, wait, I can look at other rings with this definition and it gives me something different. And that's kind of what he did. You have, let's see, this one. You have one implication though, that if A is integral, then A is almost integral as well. So integrality implies almost integrality, always, no matter what your context is. And the idea for that sort of comes from, we'll find that polynomial and then like multiply by all the denominators of your coefficients and you can get something to bring A back down. Okay, let's do examples. Why not? Any questions? Don't y'all just love a good algebra talk? I don't know if this is a good algebra talk, but it's an algebra talk. So. Okay, actually, let's look at some of these same examples. And we had this same idea, right, when we talked about integral closure. We looked at all the integral elements. We look at all of the almost integral elements. We call that the complete integral closure. And we denote that was just a prime on our domain. So we have a couple similar results. Start with the integers. We'll write out this one has complete integral closure. Again, the notation is the prime, and this guy is what we call completely integrally closed. Its complete integral closure is itself again. All right, and this one is maybe even a little bit easier to see than integral closure because, right, the quotient field here is the rational numbers. So I take something like 1/2 in my quotient field. There's no integer that's going to bring every power of 1/2 back into the rational numbers, right? Like I could try. I tried 8, and that gets me everything up through 1/2 cubed. And I take 1/2 to the 4th, and I'm back in the rationals. All right, so that's even a little bit easier to see that you can't add anything there. For a similar reason, you also get that any UFD is completely integrally closed. So again, that's a similar property. But now we'll look at some ways that they differ. All right. And so this one, right, kind of is a similar idea as the integers, right? If I take something in the quotient field K, I can write it as a fraction of elements that are in my domain, right? And then I look at all powers of this, and I'm going to have b to the n for any n, but everything in my domain is factored. So there's a most finitely many b's, or yeah, a most finitely many b's that show up, so I can't cancel all of that. Okay, let's look at this example. It's here where we start to get some stuff that is different. So look at z plus x cubed x again. And now note that my rational numbers, like 1/2, is almost integral over d, because I can just take x times 1/2 to the n. Right? Because once I multiply a rational number by x, then I'm over here and I'm okay. So I can get all my rational numbers in the complete integral closure. And so the complete integral closure is just polynomials over the rationals. Right, so that's where we get a little bit of a jump. Okay. Now, this example is one that sort of kickstarted a project that I've been working on with Jim that I sort of just recently had some answers. So we're actually finally making some progress on it. So if we look at this example again, which I guess let me just do this over here. So we're going to use this same D. It turns out that the complete integral closure is just this again. So we won't go into that whole argument, but the integral closure is the same as the complete integral closure in this case. But unlike what I just erased, the integral closure is integrally closed. The complete integral closure is not completely integrally closed. So I can take the complete integral closure again, and I can add stuff. And in particular, if I look at the double prime, so the complete integral closure of this, well, note that x brings every power of y back down into d prime. So y is almost integral over d prime. And so now I have both x and y in the second step. Right. This guy right here is a UFD, so that is completely integral closed. So that stops right there. And that sparked the question: how many steps can I do? I can do 2 with this one before I have to stop. Can I keep taking complete integral closures time after time? The answer is yes. There's at least one paper that gives a positive example, but it's kind of complicated. It starts with a group undivisibility and then says in this other paper, which is in French and I can't find, this guy has an algorithm or like a process that takes the group undivisibility to its domain. And I'm like, great, super helpful, but not really. So we're like, can we do something simpler and easier? And we believe the answer is yes. And here's at least one level up for what we have. The basic idea is we still want to end with something like this, right? We've got 2 jumps right here. So what if we make our starting place the complete integral closure of something else? So what if we try to make this D the complete integral closure of something else? And so what we do is we just create what we call the anchors that we need. So we create those elements which will bring all of, actually, sorry, we don't go back to this one exactly. We start here. Okay, we start here. We like what they did here, but it's not quite what we want. So we start here, we start differently. So, for example, say, right, we start with f, I will just call this f of x, y to the n. We won't write all the notation. So we start with that. We want all these elements to be almost integral over bringing before it, right? So what we'll do is we'll give each one an anchor. So in here, I really have x, xy, xy squared, xy cubed, and so on. So I'll do is I'll say, okay, I want a domain D, and I want x to be in D prime, right? So I'm going to call this D prime. And so, okay, if x is in D prime, then there's something in D which takes every power of x back into D. Now we're just going to give that a random name and call that x naught. And so we're going to say that we have x naught and x naught x and x naught x squared. and x naught x cubed, and so on. So this takes every power of x back in. And then we say, okay, so that gives us x. Now I want xy to be in d prime. So I need something that's going to bring every power of xy down. Call that x1. So I'll have x1, we'll have x1 times xy, x1 times xy squared, or sorry, xy quantity squared, and so on. And we'll do this for each of these. So in general, we'll say x, we have x of a, and then x of a, xy to the a, x of a, xy to the a quantity squared, x of a, xy to the a quantity cubed, and so on. So we'll add them, just add them like that. And so our general format is something like this, where a and n are both natural numbers plus 0. So we'll say that this domain that we want D looks like some arbitrary field where we're going to add on these elements, x of a is x, y to the a to the n, and a and n are natural numbers plus 0. We'll call n 0. And then sort of by construction, right, then the complete room of closure is going to have all of these guys in there. And then the next step, we get y. So this is still only 2 jumps. I took inspiration from that example with the xy to the n. We wanted to sort of reconstruct D. So this gives us 2 jumps. But then what we can do is take everything in here, give it an anchor, like we did here, give it something that sucks all its power back into the D, and then create something even bigger. So that's what we did recently, and pretty sure we got the proof down that it works. Now we're trying to figure out what special properties it has. So I don't know, that's kind of what I do with my spare time when I have spare time. So we'll stop there. I don't know what time it is. Thank you all for coming. Yeah, any questions, comments? Cool. Well, y'all enjoy the weekend. Don't do too much math. Or try to take a break. Yeah, and make sure all the pizza gets eaten. I'm gonna wash my hand. I mean, if you want to see why that works, I can always show you why, but I won't show everybody. Because not everybody wants to see.